Today we've got a nice problem from the 2023 European Mathematical Cup. And this is problem 4 of 4 from this math contest, meaning it is likely the most difficult problem on the math contest. So let's see what we've got here. So let's suppose that we've got a function f. It takes in natural numbers and it gives natural numbers. And it satisfies the following kind of interesting condition. And that is f of x plus y is a perfect square if and only if x plus f of y is a perfect square. So this squareness is maintained exactly when you move the function evaluating on the first part of a sum to the second part of a sum. Okay, so that's our setup. Now what do we want to show? We want to show that all the functions satisfying this must be injective or one-to-one functions. Let's recall what an injective function is. And that is if f of a equals f of b, then a equals b. Okay, so, well, let's jump right into it. So how are we going to do our solution here? Well, we're going to do this towards a contradiction. So in other words, we'd like to suppose that this thing is not injective, but it satisfies the condition, and then reach, some sort of thing that is unreasonable or something that is kind of obviously false. Okay, so how do we suppose that it's not injective? So let's suppose we have two numbers a and b that are different, but they evaluate to the same number inside of the function. Well, since we're talking about natural numbers here, we might as well take one to be bigger than the other. We'll take a to be bigger than b. Okay, so let's write that out. So let's suppose we have a bigger than b such that f of a equals f of b, and we might as well set this equal to something, and we'll set this equal to the sum. And we might as well set this equal to something. Let's set it equal to c. Okay, so now what we'll do is fix a natural number x, and we'll note the following calculation. And this calculation is going to make use of our given condition here. So let's look at x squared minus c plus f of b. Well, let's observe that c is equal to f of b, so in fact, these two terms cancel. So that means that this is equal to x squared, which is a square. Kind of obviously, it's equal to x squared. But since it's square, we can apply the condition and move the evaluation of f from evaluating at b to evaluating at x squared minus c. So that means we have f evaluated at x squared minus c plus b is a square. Great. And now, well, we might as well do the same kind of thing for a. So let's notice that x squared minus c plus f of a is also equal to x squared. And then this is a square for the same reason. But then, again, by our condition over here, that means that f of x squared minus c plus a is a square. Okay, nice. But now, well, now notice that we can subtract those. And if we subtract those in the right order, we get something that's positive, because we know that a is bigger than b. So let's observe the following. So now we'll look at a minus b, which is, like I said before, a positive number. But then doing that subtraction gives us what? So we'll have f of x squared minus c plus a minus f of x squared minus c plus b. But now we'd like to think about this thing over here as a difference of squares. And so let's encode that into this real quick. So let's say we're taking the square root of this and then we're squaring it. Then we're taking the square root of this and we're squaring it. So a difference of squares obviously factors in a pretty classic way. So let's perform that factorization. So here we've got the square root of f of x squared minus c plus a. And then let's see, plus the square root of f of x squared minus c plus b. And then we'll have the square root of f of x squared minus c plus a minus the square root of f of x squared minus c plus b. Okay, so there we've got that factorization. And now I'd like to observe the following, and that is that this a minus b is bigger than or equal to 1. Well, we know that because a is bigger than b. Let's also observe that is going to be strictly bigger than 1. And we know that that's strictly bigger than 1 because we've got a bigger than b. So that means this term right here in the square root is bigger than this term right here in the square root. And well, since a is going to be at least 1 more than b because those are in natural numbers, you get that that is bigger than 1. Okay, but that means we can strip it away and we'll have that this whole thing right here is going to be bigger than what's left over in this term. So in other words, the sum part of the factorization. So we have f of x squared minus c in radical plus the square root of f of x squared minus c plus b. So again, that's going to be strictly bigger than a minus b. Okay, so now let's see where that takes us. Okay, so now before we jump back into the problem, if you're liking this video, make sure to give it a thumbs up, and you haven't subscribed to the channel yet, maybe think about subscribing. It would really help us out. Okay, so where did we leave off? So I'm going to introduce a little bit of notation here. Let's set g of x equal to f evaluated at x squared minus c. That was an object that we were working with previously. And then the inequality that we had previously turns into this. We have radical g of x plus a plus radical g of x plus b is bigger than a minus b. And now I'd like to push that into a more helpful inequality for our purposes. And that is, let's start over here with the absolute value of g of x. And that's going to be bigger than or equal to 1. But it's going to be strictly less than the square root of g of x plus a plus the square root of g of x plus b. I think that's pretty clear because we're just leaving parts off that are positive. That's going to obviously make something that is smaller. But then we've just shown that all of that is less than a minus b. But now we can square these portions of the inequality that I'm underlining in green. And that's going to give us kind of an interesting inequality, which is 1 is less than or equal to g of x, which is strictly less than a minus b quantity squared. Okay, but observe that this is going to hold for all natural numbers x. So let's sneak that in there. So in other words, this function g is a bounded function. It's bounded between 1 and a minus b squared. But notice that there are only finite numbers between 1 and a minus b squared. But g of x, well, but g of x takes on infinitely many inputs. But that means that one of those finite numbers has to have infinitely many inputs pointing towards it. Okay, so, well, how could we write that out? Okay, so that means that there exists some number m, it'll be a natural number, where m is between 1 and a minus b squared, such that we have g of x equals m for infinitely many x in the natural numbers. Not all x in the natural numbers, but infinitely many of them. But now let's introduce a little bit of notation to simplify this a little bit. So what that tells us is that there exists a sequence of natural numbers. I'll say x1, which is less than x2, which is less than x3, which is less than x4, and so on and so forth. So it's an infinite sequence of natural numbers such that we have g of x sub n equals m for all n which are natural numbers. So essentially what we're doing is we're taking those infinite x, where g of x equals m, and we're packaging them together into a sequence, and we're putting that sequence in order. So this isn't strictly necessary, but I think it does simplify things a little bit. Okay, but then observe that that's equivalent to the following, and that is for all n natural numbers, we have f evaluated at x sub n squared minus c equals m. That's just because we're defining g exactly like that. So that's just stepping back from our g function to our original f function, which is the function that satisfies this condition over here. Okay, so now here's a really important step that we're going to do. So let's take some fixed number y, and that fixed number y will be strictly bigger than the square root of m. And then we're going to look at an expression that we can apply our condition over here to. So let's note that y squared can be rewritten like this. So it's in fact equal to y squared minus m, and then plus f evaluated at x sub n squared minus c. Essentially, we're just adding and subtracting m. So notice that this is most definitely square because it's y squared. But now we'll use our condition over here to take the evaluation of f and move it over. So that tells us that f evaluated at y squared minus m plus x sub n squared minus c is also a perfect square. So since it's a perfect square, well, we can name it a perfect square. And this perfect square, let's set that equal to zn squared. And that is with zn a natural number. And well, why does it depend on n? Well, that's because the left-hand side over here also depends on n. And so we're getting a different perfect square for each one, but we are getting a perfect square. Okay, so now where do we want to go from there? Well, let's observe the following. We can write f of y squared minus m minus c as z sub n squared minus x sub n squared. But now notice that since this y here is fixed, that means this left-hand side of this equation is also fixed. In other words, the left-hand side of the equation is constant. But observe that the right-hand side of the equation is holding for all natural numbers n. Then likewise, or I guess importantly, this xn squared is always changing. And that's because they're always taking on different values. But then if the left-hand side is fixed, the right-hand side also has to be fixed. But the right-hand side being fixed, if one part of it is changing, means that the other part is the same and it cancels out. So that means that these cancel out to 0. But then if that's 0, we can rearrange this equation and we'll see that we know that f of y squared minus m is in fact equal to c. But let's observe that we did fix our y here, but we fixed it arbitrarily. And since we fixed it arbitrarily, that means, in fact, for all values of y that are bigger than the square root of m, we have f evaluated at y squared minus m is equal to c. In other words, we have the following condition. For all x bigger than radical m, f evaluated at x squared minus m is equal to c. Okay, so now that we've got that taken care of, let's see where we can go. Okay, so let's review some parts that we have so far. So we started with this a bigger than b and f of a equals f of b equals c. And then we found this value m where f evaluated at x sub n squared minus c was equal to this m for all values of n. So this is the thing where f, or infinitely many inputs into f gave us this number m. And then we also showed that for all x bigger than the square root of m, we have f evaluated at x squared minus m equals c. And then very, very similarly, you can prove that f evaluated at x squared minus c equals m. I'll leave that as a bit of a homework exercise. And now we've got this technical lemma. And we're going to show that there is a capital M where every f of z is either less than or equal to this capital M, or f of z is congruent to that lowercase m plus 2 mod 4. So like I said, this is a technical lemma, but this will help us finish everything off. Okay, let's get going with that. So let's start with the first case where z is of the form x squared minus c. But that tells us that f of z, well, that's pretty clearly equal to f of x squared minus c, but we showed that that was equal to m. I guess assuming that x is large enough, which we're implicitly assuming here. We can always kind of assume that it's large enough because for all of the smaller values, we can just smush together here in the kind of boundedness. Whenever you're talking about boundedness, you only really need to work with the tail of a function. And now that's good because if we've got this m right here, well, f of z is less than or equal to this m in this case. Okay, so now let's move on to the next case, which is z is not equal to x squared minus c. In other words, z cannot be written as a perfect square minus this number c. Okay, now let's take a number y, which is bigger than this square root of m, which we've been working on and off with the whole time. And let's observe that if we take f of z plus y squared minus m, we'll see that if this is a square, then that would imply that we could move the f over and have z plus f evaluated at y squared minus m is also square. And what we're going for here, I should say, is that this object right here is not a square, and we're working towards a contradiction. But notice that f evaluated at y squared minus m is going to be equal to c by this condition right here. So this means that z plus c is square, just by making that replacement. But then that means that z plus c equals x naught squared with x naught being some number. And that's because, well, all squares can be written as the square of some other natural number. That's the definition of a square here. But observe, that means that z is in fact a perfect square minus c, which is what we were assuming not to be the case right here. So that leads us to a contradiction, meaning that this object right here is not a perfect square. Okay, so let's recall in this case, we showed that f of z plus y squared minus m was never a perfect square. Now let's move some things around. And that means that this number f of z is never equal to something of the form x squared minus y squared plus m. So again, that's just by moving some things around. This might look kind of weird, but notice that's just a difference of squares plus our number m, which we constructed several steps ago. Okay, but now what does this hold for? So this holds for all natural numbers x and then numbers y that are bigger than the square root of m. Well, let's maybe go ahead and take the smallest y where this occurs. So let's set y1 equal to the smallest y, which is bigger than the square root of m, making this not equality happen. So putting that together, what do we have? So we've got f of z is not equal to y1 plus 1 squared minus y1 squared plus m. So again, we're taking the smallest y, and then we're setting x equal to that y1 plus 1. But observe that we can do a calculation here that's pretty straightforward and see that this is 2 times y1 plus 1 plus m. Okay, so just to reiterate, what we have here is that this f of z is not equal to something of this form. But that means one of two things. So that means that either f of z is less than this object right here, 2y1 plus 1 plus m, or f of z is not congruent to m plus 1 modulo 2. Okay. And now we're going to play essentially the same kind of game, but with a different choice for x. So let's also notice that f of z is not equal to this y1 plus 2 squared minus y1 squared plus m. But then expanding that out and canceling, you'll see that this is 4y1 plus 4 plus m. And then we can break that into two cases as well. And so one case will be the inequality case, and one case will be the not congruent case. So that means that f of z is either less than 4y1 plus 4 plus m, or f of z is not congruent to m modulo 4. So let's put this all together. So either f is bound above by, well, notice that it's this number right here, and that's that number right there because that is the larger of these two numbers that we have the bounding, or f is not congruent to m plus 1 mod 2 and f is not congruent to m mod 4. But being incongruent to both of those things is exactly the same thing as being congruent to m plus 2 mod 4. But that finishes the proof of this lemma. Okay, let's see how we can take this to finish off our problem. Okay, so now we're ready to finish this thing off. So what we'll do is we'll pick a natural number w satisfying two conditions. And those conditions are that w plus 1, w plus 2, w plus 3, all the way up to w plus m are not perfect squares. So perfect squares become arbitrarily, largely spaced out. So it's pretty easy to pick these not to be perfect squares by picking w carefully enough. And then the next condition will be w plus little m is congruent to 0 modulo 4. And again, well, we can always make these two choices. Okay, so we've chosen w like that. And recall our little m was defined before, and our capital M comes from the lemma. I should say that. Okay, so now what we'll do is we'll take a number d, which is bigger than the square root of f evaluated at w. And let's observe the following. And that is that we can take d squared and write d squared as d squared minus f evaluated at w plus f evaluated at w. And observe that this is fairly obviously a square because it's d squared. But also it's something that is set up so we can use our condition over here. And well, that's exactly what we'll do. We'll take our evaluation at f and move it over. So this shows us that f evaluated at d squared minus f of w plus w is also square. We've taken that evaluation of f at w at the end and moved it over. Okay, so now let's apply the lemma to this input here, d squared minus f of w. And we'll set this d squared minus f of w equal to z. Okay, so that tells us one of two things because notice that the lemma is an or statement. So we either have 1 which is less than or equal to f of z, which is less than or equal to m, which adding w to all parts of this we'll see that w plus 1 is less than or equal to f of z plus w, which is less than or equal to w plus m. But let's observe that this is not possible because none of these are squares. So I'll just put here that this is not possible. Again, because, well, notice that this right here is f of z plus w, which we proved was a square, but now we've got this f of z plus w is part of a list which we're choosing to not be square. Okay, so if this is not possible, then that means that the other part of the conclusion for the lemma must be the thing that is true. In other words, we have f of z is congruent to m plus 2 modulo 4. But then let's now observe that f of z is in fact equal to a perfect square minus w. And that's by this line right here. But moving the w over, that tells us what? That tells us that m plus w is congruent to a perfect square. I'll just put box square here, plus 2 modulo 4. But then perfect squares are always congruent to 0 or 1 mod 4. But that means that this whole thing after adding 2 is either 2 or 3 mod 4. But let's look up here at our assumption that w plus m was 0 mod 4. So that means this possibility is also impossible. In other words, we have reached our contradiction. And that's a good place to stop.